Hello, Namaskar again. So now in this lecture I would see about potential energy due to in an external field. So already we have seen about calculating the potential energy for a system of charge, and then what is the difference? So the difference here is that we are using the external field. Like you remember that when we are constructing the system, we are bringing the first charge, and then there is no potential because there are no charge, no external field. But in this case, even when you are bringing the first charge, there is a external electric field exists there. So it means there is a potential already, and then that we are bringing that system in when we are bringing the charge from infinite to that point. So already there is a potential exists, that is external potential, external electric field. Because of that there is external potential, and then you are estimating that. So the sequence and the concept will remain same. The only one term will be added where we are will be estimating the potential energy due to the already existing potential, and then we are building the system. So let's see, once we are doing it will be becoming more clear. So let's have a look at it. So when we are saying let's say we want to build a system of two charges, right? So let's say it is Q1 and this is Q2, and then it means then when you are bringing it from infinite and from infinite to this point, so some work have to be done, and that work will be based on the potential at that point. So let's say this is your point R somewhere. This is represent position vector R1 for this and position vector R2 for this, right? So it means that if you are bringing the very first charge, and there is already exist a potential at let's say vector R, so it is potential at R1 is vector R1, right? So at this position vector the potential is this, then you already have a potential. So when you bring the first charge itself, you have to do some work, and that work will be Q1 into V at that position vector, what is the potential, right? So earlier it was 0, but now we have already a potential electric field there, so there we have to work have to be done, and that work would be equal to this, and that of course as per the definition this would be the potential energy at that point for the charge Q. Okay, and important point, as you know that work done that is represented QV, and we also write it joule. So it means that if you bring a 1 unit charge from infinite to that point, so your Q, and then the potential at that point, let's say 1 volt, delta V is 1 volt, right? So it means that an electron, if this charge is electron charge is what, 1.6 into 10 power minus coulomb. So 1 electron is associated with the voltage difference of 1 volt. Then what would be the energy, the work done? That would be the potential energy. So that would be given as Q delta V, and that would be what, 1.6 into 10 power minus coulomb and into 1 volt. So that would equal to 1.6 into 10 power minus this is 19 joule. This is also written directly as a 1 electron volt also, right? So whenever we talk 1 electron volt, it means that 1.6 into 10 power minus 19 joules. So that's the important conversion you can have. And similarly we can have joules, gigajoules, megajoules, as per we follow that 10 to power 10, 10 power 9, 10 power 12 depending upon the requirement. So this is some conversion when we are using electron volt or joule depending upon that. But now let's actually calculate that the potential energy for a system of two charges when we are bringing that from infinite to that point, and that will I think clear and make the differentiation clearer from what we have studied earlier. So let's see. So let's say we want to build a system of charge which having two charges Q1 and Q2, and the position vector is given as R1 and R2 for that, right? So R1 and R2 are the position vector for this point. So let's say when you are bringing the first charge, right? So you have to work done from infinite to bringing to that for even first charge, what will be the work done? So let's say that is W1, and that would be Q1 into V at R1. Okay, and then you are bringing the second charge. So when you are bringing the second charge, so there is already a potential exist at V2, that is VR2, that is external due to external field. we can call it due to external potential due to external charge. So this is potential there. So the work done for that would be how much? The total potential would be how much? So that already there. So it will be VR2, okay, plus potential due to charge Q1, and let's say this is the distance between these two, and that is distance is R12, right? So you can have a potential 1 upon 4 pi epsilon 0 into Q1 Q2 upon R12, right? So total potential here, that would be algebraic sum as we follow. So total potential Vt equal to VR2 here plus 1 upon 4 pi epsilon 0 Q1 Q2 upon R12, right? So what would be work done if you are bringing a charge, a unit positive test charge from infinite to this point? So that would be multiplied by the charge, so it is Q2. So the work done W2 in that case would be Q2 into Vt, that total we just calculated. So it would be here to Q2 into VR2 plus 1 upon 4 pi here this, sorry, here the potential is due to Q1, right? So this will be only Q1, not Q2 here, right? So it will be 4 pi epsilon, and then here it will be multiplied by Q2 into Q1. So this is the work done, and the total energy of the potential energy of the system will be the total work done for constructing this a system of two charges. So the total work done would be your potential energy of the system, and that would be the sum of W1 plus W2. So that can be written as how? So that you can write as Q1 V R1 plus Q2 V R2 plus 1 upon 4 pi epsilon 0 Q1 Q2 upon R12, right? So this is the difference here, right? The even first charge you brought, there is external field, and that based on that field we will have the total work done, and that would be the potential energy of the system. Okay, so this is about two charge potential energy. So in a summary, you can write that that potential energy of the two charge system would be you can write equal to Q V Q1 V1 VR1 position, what is the potential at R1 position, vector position, and then Q2 VR2, and then the sum of this due to charge Q1 at point Q2, right? So this is the potential energy for a system of two charges. You have an equation now. Now let's proceed further, and let's say you want to calculate what would be the potential of a dipole. So that is also no two charge system, but there is one positive, one negative, and we already have studied about calculating electric field due to dipole at different places and all different points. But here we are assuming that there is already an uniform electric field exists where there is a dipole, and then you are constructing that dipole, and then what would be the potential of that dipole in an external field. So let's calculate. Okay, so let's assume that this is your uniform electric field. Okay, and now let's say this is your charge Q minus Q, and here your other charge plus Q, and as we represent it, it would be represented by the dipole moment P, and let's say this is the angle with the electric field theta, and this is the electric field direction, of course, and then you will have this is let's say the center here, so it is A, the total distance is 2A, so it can be written as here as 2A A cos theta here, and this distance would be what? This distance would be minus A cos theta, alright, and let's say this is your x direction. Now already we know that what would be the torque in the external field on the dipole, so that can be given as tau is equal to P cross E, that is the vector which we know. Now consider that Q1 is equal to your plus Q, so this is your Q1 is equal to plus Q, and Q2 is equal to your minus Q here in this case. Now we want to calculate that what will be the potential energy of the dipole at external electric field. So now, as we know that in a dipole the forces work here in two different points, but they are equal and opposite, so they are neutralized. But we have a torque here, right? So assuming that that torque, due to that it tries to align in the direction of electric field, the dipole moment. So let's say we apply an external torque to neutralize that force, and then to maintain in that in a particular direction, and we need to calculate that if you want to rotate from theta 0 to theta, then what work have to be done, right? So in that case, to calculate that work, you can write that rotating from theta 0 to theta 1 angle, tau external is the external torque applied, and this is the d theta. So this is how you can utilize that calculation of the work done, and that would be the potential energy of the dipole, right? So this can be written as theta 0 to theta 1 Pe sin theta d theta. Now you integrate it, and then you will get Pe bracket cos theta 0 minus cos theta 1, right? So as we know that this work done from system itself, from a point to other, always depend upon the initial and final position, and it doesn't depend upon path, right? And also it allows that you can add the arbitrary constant to the potential energy at a given point, and then that doesn't change the potential difference between the two, right? So assuming that we are rotating that the angle from perpendicular to some angle theta. So let's assume that if theta 0 is equal to pi by 2, we see that how we can justify in our the regular calculation which we did for the above two charge system. But let's say if this is the so, then what we can have. So then we can write here if theta 0 pi by 2, we can write Pe cos pi by 2 minus cos theta, let's say. So you want to bring in from pi by 2 angle to some angle theta. So this can be written as can be given like that. So if cos pi by 2, then it will become 0, so it can be written as minus p cos theta, or you can write it minus p dot e, dot product of the two. So this is how you can calculate the potential energy to rotate work done to rotate it from some perpendicular to electric field to that some angle theta, and that will be the potential at angle rotating an angle theta, and that can be written as u theta is equal to minus p vector p dot e, the dot product. So this is a very important formula you got for calculating the potential energy for a dipole in a external field. Now coming back to justification and following the similar which we just did above, how to do this in this case. So in this case again, now you can calculate potential energy for a system of two charges, minus q plus q in some point. So you can write the same thing, potential energy, as we just followed for two charge system. So again the charge is same, but potential will be different for two charges that negative positive. So it can have a potential at R1 minus potential at R2, right? And then you have a q square, q1, q2, that is q minus q is equal to minus q square upon 4 pi epsilon 0, and they are separated by distance 2a. So this is what you can get once you follow the other formula we just showed, this one, right? So with this formula you can calculate for the dipole again, we did above. And now you can denote the position vector r1 and r2 there, and then the potential work done, the potential between the 2 points would be what? This is the potential difference between the 2 point delta V, and that can be equal to how much? That can be equal to that the energy required. So it can be your potential difference between the 2 points can be given as R1 minus V at R2, and that can be equal to QE, right? So QE, so coming back to this figure again, so the displacement between these two, like no, it is like separating these two charges the potential between these two, it means that bringing the two charge from infinite to these two places. So the potential difference between these two will be given by the electric field, which is the displacement between these two, right? So the displacement between these two is that 2a cos theta here, this way, 2a cos theta, the distance, and the electric field the opposite direction of the displacement in the opposite direction, right? So let's say I want to bring the charge this q2 to q1, right? So the potential difference will be given as v r1 here and vr2 here, okay, right? So vr1 minus vr2 can be given as minus e into 2a cos theta. That we can write, not a problem. So it can be written as minus e into 2a cos theta. Okay, so it means you can write the same thing here and then just place that point. So you will become minus 2e into 2a cos theta minus q square upon 4 pi epsilon 0 2a. Okay, so it means q into 2a becomes p, so you get minus p e cos theta. You got the same thing, minus q square upon 4 pi epsilon 0 a. Now you see, for the given system, this is the whole constant, and we know that adding or subtracting a certain constant, potential energy doesn't matter, because that depends upon the initial and final question. So that's bring the arbitrary choice, choosing that theta 0 is equal to pi by 2, which is just equivalent to this. So if we neglect that and considering the point adding a certain value to that, so it can be written as minus pe cos theta. That we arrive to the same point. We can have minus p dot e is equal to at angle theta, if they are separated with the angle theta with the electric field. So that would be the estimation. So this, you can see that in both ways we got the same potential energy as we calculated before, utilizing the torque concept. So this is all about estimating the potential energy for a two charge system in an electric field, and also for the dipole in the two method, and that's really an important formula I came across. You can utilize now this formula to calculate many physical problems, and we'll see in some coming chapters, some coming examples in our coming lecture. So there we'll discuss. So this is all for now. Now we'll discuss again in the next lecture about electrostatics of conductor. So see you there. Thank you.